I'm happy to be here. Thank you for the invite. I'm from Texas A&M University, which is not in Austin, but another great location. That's the town which is called College Station. This presentation is going to be more on the fundamental side. And the question we are asking, what is the effect of the molecular interaction on or architecture on interactions of water-soluble polymers and polyelectrolytes? So different molecular architectures, other than linear, are ubiquitous in nature. And fundamentally, we know that as you start introducing branching in a polymer chain, so you're going to cause a compaction of the polymer chain, which can be described by the degree of compaction, the density of the coil or polymer increases, and eventually it can be predicted for neutral polymers. This was done by Kramos and Douglas, that at the degree of functionality 20, you get a transition from the branched to particle behavior. So definitely in this kind of polymers, you have enhanced segmental density, and all fundamental properties such as diffusion, mode of diffusion, macroscopic behavior, viscosity are drastically changing compared to linear polymers. And also on a practical side, so we would expect that the drug encapsulation or capacity or interaction with small molecules, it's going to be altered also. Again, to answer a broad question of how the star polymers are different from linear chains, so we are looking at them, these differences in solution and within the films. And you're going to see here a little bit different stories. One will address the behavior of star polymers in solution, which also will have two small subsections, UCST, temperature responsive stars, and polyacid pH responsive stars. And then we're going to put this stars in the layer by layer films, and we'll look at how this architecture alters the dynamic structure of the LBL films and response to salt. So let's start from the first one. It's UCST polymers. The most common UCST polymers are not that easy UCST behavior to achieve in aqueous solutions. We know that, and this is because of the notorious tendency of water to cluster within this hydrophobic lake or ice-like structure around polymers, and LCST is more common. But there are polymers such as PNAGA, which forms hydrogen bonding, or some zwitterionic polymers, which form electrostatic bonds. And these kinds of interactions, when you introduce them in the polymer assemblies, they show the UCST behavior, which is basically the endothermal behavior at higher temperatures. You're going basically to dissolve, to disrupt this interaction, get more classical UCST type phase diagram. So in our work, we're going to look at the chemistry, which is based on the uredo modification of our polymethyl methacrylate based chain. And we start from basically the amino functionalized polymer and then convert it to the uredo moiety. So we make stars, right? So we start from cores which are polyols, and the favorite core we start from is the pentaerythral, and then we extend it, we introduce the bromine group, and then we follow with ATRP. So when we do ATRP, we have to protect our side group or monomer side group with BOC. Then we remove the BOC protection. We are left with amino group, and we follow with the uredo modification. Here is an example of how we got a 4-star UCST polymer. So the challenge is to characterize the branch architectures. And so this is actually an enjoyable physicochemical project for students. So if you just write around the GPC, you're getting a faster illusion of linear polymers because they are just hydrodynamically, they take more hydrodynamic volume, and the 8-on polymers are more compact, but it's very hard to match the molecular weight. And you can make conclusions only when you exactly match the molecular weight. And my student Alexei did a great job. So we now get a linear form 6-on, 8-on polymers with pretty well matched molecular weights and narrow monodispersity. Polydispersity index is below 1.1. And to determine branching, you need to use, as many of you know, 2 different techniques. One is hydrodynamic, and this is a multi-angle light scattering equipped with viscosity detector. And then you need to do a classical the light scattering, static light scattering, to determine the absolute molecular weight. And if you put these results together, so you are going to see that the branching ratio, branching per molecule, was pretty consistent, and we got a good set of polymers with 4, 6, 8 branches. And again, an important thing to remember that they all have the same molecular weight. So we are doing our core first polymerization, and we match molecular weights. So one of the questions people ask in this area is how the branching architecture affects the UCST behavior. And we were a little bit disappointed that we didn't see really a strong effect of the molecular architecture at this low degree of branching on the transition temperature, the phase transition, which was within the arrow. However, as expected, as you increase the molecular, the polymer concentration, you're going to increase the transition temperature again, according to the theory. So, but what is actually significantly affects the intermolecular bonding and the transition temperature is the addition of the hydrogen bonding competitor. So the UCST behavior which was observed is due to internal hydrogen bonding, which is shown here on the schematics. And as you start adding DMSO, a competitive hydrogen bonding solvent, so you're going to form a competitive hydrogen bonds between SO and H moieties, disrupting this internal hydrogen bonding and therefore decreasing, suppressing the UCST transition, which was interesting to observe. So finally, so we thought that, the stars should be good for something. And we started the capture of different drugs or model drugs or dyes within the course. And here is a proflavine. It's a dye which we use as a model dye, which is easy to track using fluorescence. So we added those proflavine to the polymers, followed by precipitation and measurement of the remaining of the drug in the supernatant. And basically the conclusion is that of course, the denser or high density of polymer segments does matter, and you're going to capture, you're going to have a high load of this dye within the core. So the architecture does matter. So I'm going to switch from UCST stars to polyacid stars, a similar strategy, but now the monomer is going to be acidic and very simple. And in this case, we are having the carboxylic group. It's very convenient to covalently trap it, tag it with a bright fluorescent dye Alexa, and follow with fluorescent correlation spectroscopy and other fluorescent techniques we have in our group. So now again, we have a series of linear two-star polymers with exactly matched molecular weight, but varied architecture. But now these molecules are acidic, weak acids with fluorescent tags. So on the left, you will see the FCS fluorescent correlation spectroscopy results, which are done in extremely dilute solutions. Down to several molecules in the cubic micron. The dependence on pH is interesting. You definitely see that at a higher pH, the linear chains are more expanded as expected. So lower density of segments, higher expansion as you decrease pH, however. So all curves collapse to the same curve. And this is because at the low pH, the internal hydrogen bonding between the carboxylic groups sets in. And this actually masks the differences in the hydrodynamic sizes. They all become relatively compact. So the next thing we did, so this graph on the left was performed at extremely dilute solutions. And then we moved on to look at the solution regimes of star in linear polymers. And the graph in the center is made when we were mixing the fluorescently labeled molecules with unlabeled one. And we achieved we went to high concentrations going from this extremely dilute solution to the semi-dilute. And as we go to the semi-dilute solution, there is a pronounced and well-known kink. So, or in the diffusion coefficient calculated from FCS. And you can see in at low salt concentration, so the data, as you see, are quite surprising. So if you think about the more compact structure of the star, C star should be higher, but here you see the inverse trend. The C star for the linear is higher. And this was a big surprise. We actually repeated it several times, thought it's something wrong with the synthesis of molecules. And when you do see it in your observations with polyelectrolytes, you're saying, you know, let's add some salt, go to the neutral chain regime and see whether there's a problem with our synthesis. So we do the same. These results were done in the buffer condition of 10, 5, 10 and minus 3 molar. So we did the same. We repeated the same experiment in high salt condition, and now things became normal. So as expected, the more compact star polymers basically showed a higher C star transition, which kind of gave us a peace of mind. So what this result actually means is that, first of all, we have an inversion of the dependence on C star on the molecular architecture in different salt regimes. And while the high salt behavior is well understood and follows the existing theory, so what is happening at the lower salt is unexpected and interesting, and we think this is we have a switch of the diffusion mechanism, and in the semi-dilute regime, probably the star is moving. Stars are moving through retraction of the arm, and I think this new mechanism contributes to the extension of the arm. I think it occurs in the transition region in the C star regime. We don't understand it yet. We are talking to Dobryny to try and do additional experiments and publish a paper on that. So we're going to now go to another part of my talk, which is the layer by layer film. So we traditionally like coatings. We like to introduce different molecules within the coatings to produce functional materials for mostly biomedical applications, and my group was active in making bioactive coatings and drug delivery coatings for slow delivery. So what I'm going to show you, it's still mostly fundamental. So we are just at the very beginning. So we took our UCST stars and put them in the assembly with PMA at pH 4 at the surfaces. And the graph on the top, it's the linear or assembly of the linear chain, which gives you kind of a messy surface AFM morphology and very nice, well, distinct stop architecture on the bottom. So, and when you actually study the capture of fluorouracil and gallic acid, you consistently get the results that the star containing films are definitely better in capture of small molecules, even at the surface, which means basically that the binding molecule does not prevent, doesn't suppress the high density, the ability of the high density units to interact with small molecules. So the other thing which our group is traditionally interested very much is the dynamics of polymers in LBL films. It's a fundamental question of when we actually make the films with layer by layer assembly, sequential assembly. So whether this layering stays or it evolves, and how it evolves in different environments. So you can observe dynamic of polymer chains in during LBL assemblies using ellipsometry. This is what is shown in this graph, measuring the wet thickness as a function of deposition, and you can learn a lot. And another one technique, which is usually, we are using routinely, it's the post-assembly LBL assembly. So we assemble the films, and then we're applying neutron reflectivity to look at the internal interfacial thickness. So finally, we also have a fluorescent recovery after photobleaching technique, and neutron reflectometry and fluorescent recovery after photobleaching are measuring dynamics in two orthogonal directions, while the neutron reflectometry looks at the diffusion of the chains perpendicular to the substrate. With FRAP, you're going to look at chain motion in the direction parallel to the substrate. So we are doing this experiments with John Ankner at Oak Ridge National Lab, and here is the schematics of how we do the experiments. So we build the films of two stacks. So we put the molecules, the star molecules on the bottom, and add, in this case, the deuterated polymer, linear polymer, I'm sorry, hydrogenated linear polymer, and then continue building the upper stack from also hydrogenated star polymers and deuterated linear polymer. So the scattering length density of the upper stack is going to be enhanced due to the presence of this deuterated linear polymer. So when we are getting our results, we analyze them, and you can see that SLD, scattering length density, from this gray stack, the top stack we are depositing is going to be higher. And we're going to see a transition between the deuterated and hydrogenated material from the behavior of this intermediate region, which we call traditionally in neutron reflectometry, this is called roughness. It's not the external roughness, but it's the internal roughness related to diffusivity. We are going to see and observe the rate of the degree of penetration and the rate of penetration of the top layer to the bottom. So here is the chemistry of the polymers we are using, and the graph on the top shows the scattering, the SLD profile for the film composed of linear polyacrylic acid. This is the experiments we done with acidic stars. So you can see that the internal roughness is relatively low. So you do the same after deposition and drying of the film. So you get a higher interpenetration with stars. So this internal roughness increases systematically, so as probably expected. But there's always an argument. Is it due to diffusion? Is it just due to different roughness, or due to more compact morphology of star polymers? So to answer this question, so we need to do the experiments as a function of salt. The previous profile I showed you were obtained in low salt conditions, where the translational self-diffusion of the entire polymer chains was inhibited. So the polymers are trapped in non-equilibrium conformations. So what we are doing now, we are adding salt, 0.45 mole of salt, and we expose our films to salt. We are doping the ionic pairs with the externally compensation of the charges through ions, and this promotes, this doping promotes the chain diffusion. So you can see that in the case of linear polymer acids, so however, the evolution or diffusion of chains just visually was slower than in the case of the stars. So we can apply the limited source model and actually quantify this dependence. And by plotting the C naught versus CT, C naught is the concentration derived from the SLD in the beginning of the experiment, and CT in the plateau region of the deuterated stack. CT, it's change of the concentration of deuterated species after time t. So sigma naught is the original internal roughness. So we can fit the data. So, and we actually conclude, we can calculate from this dependence the diffusion coefficient, and it's clear increase in the salt-induced diffusion coefficient in stock-containing films by at least 1 order of magnitude. So which is, or answers the question that it's not just the roughness is different in the film containing the stars, but they do diffuse faster. This also argues against some models which show that the stars interact with linear polymers through entanglements with the core of the star polymers. So finally, we do fluorescent recovery after bleaching experiments. And in this case, we label polyacids of different molecular architecture with the Alexa dyes, and look at the lateral diffusion or self-diffusion of the polymer chains. So with the photobleaching and photobleaching experiments, you start from initial film, you apply a laser beam with high intensity, you bleach the spot, then you switch the beam to a lower intensity to observe, not to bleach, but to observe the events, and you see how the fluorescent intensity slowly recovers. And of course, you calculate the diffusion coefficient from this data. So we can see the raw data on the left and the right. They show strong dependence and strong influence of salt on diffusion of both linear and star polymers. And if you plot the data in the semi-log form, so as a function of log of diffusion coefficient as a function of C or concentration of salt, you get basically two families of the dependence. So you see that the slope of this dependence is much higher for stars, right? So, and it's the linear assemblies are more sluggishly responding to salt. This again reflects a completely different mechanism of star diffusion versus linear diffusion. And you can see that even when you switch from 2 to 4 arms in the polymer chain, so you already see a very significant difference in the diffusion and the dependence of it on salt. The second thing, how to think, or second way to think about polymer diffusion was actually developed by Joe Shlonov, and he considered the Hoppin model of polyelectrolyte diffusion. So basically a very intuitive picture that the polyelectrolyte chain moves to hopping of the segments or several adjacent units in the polymer chain. And from this model, a little bit different scaling follows with the diffusion proportional to the salt concentration in the power of lambda. Lambda is called length, but in reality, it's just the number of polymer segments involved in a single hopping event. We looked at also how this model fits our data, and the fit was actually equally good with a similar trend. So the interesting thing is that you can recover lambda, or how many segments of polymer are hopping during salt-induced motion. And naturally and interestingly, so that number sharply increases for the stars. So it's about from 3 to 4 segments involved in the hop during diffusion. So in the case of stars. And this is due to, of course, increased connectivity and dependence of the interdependence of the hopping of the segments in their branched or star-like architecture. So this brings me to probably a little earlier, but it brings me to the end of my talk. So I talked about 3 different topics. One was our major conclusions is that that the first one is that the temperature responsive star polymers have the enhanced trapping capacity of model drugs. We find a very interesting inversion of the C-star dependence as a function of salt for linear and star polyelectrolytes. And we look at the role of molecular architecture in dynamics of assembled LBL films and find a fundamental, I think, observation made for the first time that the star-containing polymers are dramatically more sensitive to concentration of salt compared to linear polymers. So with that, I would like to thank my current group and very recently graduated members and new coming. But this is this guy, Alexei, from Belarus, who basically produced most of the experiment for this project. And this particular project was funded by the National Science Foundation Department of Materials Research, Division of Materials Research. Thank you very much. I will be happy to answer your questions.